Hello, and welcome to Linear Algebra. This is lecture 30 on the QR decomposition. So last time, we talked about isometries. So these are linear isomorphisms that preserve the length of vectors. We saw that if we're working with inner product spaces, then isometries are also the same as maps that preserve the inner product, as isomorphisms that preserve the inner product. This time, we're going to talk about a decomposition of matrices. So previously, we've talked about the LU decomposition, where we had lower and upper, so lower triangular and upper triangular. This time, we're going to have QR. So the Q is going to be an isometry, and we're going to compose it with an upper triangular. So R stands for right. So you can think of it as a right triangular matrix. Sometimes you see QU, and U stands for upper triangular. Okay, so let's start by recalling. Like we just mentioned a moment ago, a linear map is an isometry if it is an isomorphism and it preserves the length of vectors. For VW finite dimensional inner product spaces, this is equivalent to knowing that the vectors T of V1 through T of Vn form an orthonormal, an orthonormal basis of W whenever V1 through Vn is an orthonormal basis of V. Also equivalently, if BV and BW are orthonormal bases of BW respectively, then a linear map between V and W is an isometry if and only if the matrix associated to T with respect to these bases has orthonormal columns forming a basis of Fn. Okay, so those are different ways of recognizing that a map is an isometry. Okay, so next we want to relate this to a property of a matrix when you take the adjoint. So remember that if you use real numbers, then the adjoint is the same as the transpose. So let's make this a proposition. The columns of a matrix A of size, well, let's go ahead and do square matrix of size n by n are orthonormal if and only if A star A is equal to the identity. Okay, so this says that if the columns of a matrix form an orthonormal basis, then the matrix is invertible. That's not surprising. Matrix is invertible if and only if the columns form a basis. But the inverse is given by the adjoint of A. So that is new. Okay, let's prove this. So let's write A as being the matrix with columns alpha 1 through alpha n. Then A star will have rows given by alpha 1 conjugate through alpha n conjugate. Okay, so complex. Okay, so here, because we're using bars for vectors, you may not notice that this bar is different. But this bar refers to the complex conjugate. So what we're doing is taking this column, we're writing it as a row, and then we're taking the complex conjugate of each of the entries. Okay, so beware the notational overlap there. And A star A, okay, so what are the entries in A star A? Well, you have alpha 1 star alpha 1, alpha 1 star alpha 2, and so on until you get to alpha 1 star alpha n. Then this would be alpha 2 star alpha 1, alpha 2 star alpha 2, and so on until you get to alpha 2 star alpha n, and so on until you get to alpha n star alpha 1, alpha n star alpha 2, and so on until you get to alpha n star alpha n. Right. Those are the entries. And so A star A is equal to the identity matrix if and only if, when you do alpha I star alpha j, you get either 1 if I is equal to j or 0 otherwise. And that's the same as saying that these columns alpha 1 through alpha n form an orthonormal basis. Of Fn with respect to the standard inner product. Right, because the standard inner product of alpha I with alpha j is precisely, well, actually, this would be the inner product of alpha j with alpha I is alpha I star alpha j. Okay, wonderful. So that's a way of recognizing if the columns of a matrix are orthonormal. It's just is A star A equal to the identity matrix. And recall that's one way of determining if the map's an isometry. So that's important enough that we give it a name. So if you have an n by n matrix with complex coefficients, we say that it is unitary. Let me write that. Is unitary if A star A is equal to the identity. If you have real coefficients, the same concept gets a different name. We say it's an orthogonal matrix. If A transpose A is equal to the identity. right? And so let me write out explicitly, if you have a complex matrix with real entries, then its adjoint is the same as its transpose. So a unitary matrix with real entries is an orthogonal matrix. Okay, so we're really talking about the same concept. We just give it different names when we have different coefficients. Right, and the thing to note, as we already noticed, if you have a unitary matrix, then the inverse is the adjoint. So it is very easy to compute. Okay, let's do an example. Let's look at the 2x2 matrices. It is easy to find all possible orthogonal 2x2 matrices. All right, so you have A, B, C, D, say. So let's start by looking at the first column. So if we're going to have an orthonormal basis from the columns, then the first column, B, must be a unit vector. So A squared plus B squared is equal to 1, and that's the same as saying that the point AB is on the unit circle. Now, every point on the unit circle corresponds to some angle theta. So we have cosine theta, sine theta for some angle theta. Okay, so we've found the first column, cosine theta, sine theta. The second column must be a unit vector orthogonal to cosine theta, sine theta. Okay, so there are two choices. Right, so we're going to take minus sine theta cosine theta, and the other possibility is sine theta minus cosine theta. That means that the matrix is either, well, you could have cosine theta sine theta minus sine theta cosine theta, right, which we recognize as the matrix associated to rotation by theta in the standard basis, or the matrix is cosine theta sine theta minus cosine theta, which we recognize as cosine theta sine theta minus sine theta cosine theta times 1, 0, 0, minus 1. Right, so here we have again the rotation by theta, and then this other matrix is reflection across the x-axis. right? So this matrix corresponds to the linear map that does nothing to the first coordinate, but changes the sign of the second coordinate. So just by this short exercise, we conclude that every linear map from R2 to R2 that preserves the length of vectors is either a rotation or reflection across the x-axis followed by a rotation. Okay, so those are the only maps that preserve the length of vectors. Okay, wonderful. So now let's move on to the QR decomposition of a matrix. So here, I'll just say the so-called QR decomposition of a matrix is useful in numerical linear algebra. So for example, we talked last time about how, I don't know if it was last time, we talked previously about how it's useful to have a notion of the norm of a matrix because if you're solving AX equal to B, then you're multiplying, so you can solve that by saying X is equal to A inverse times B. And so any error that you have in determining B gets scaled by the operator norm of A inverse as an error in determining X. So you can talk about how stable is it to solve the system by multiplying by A inverse. And it turns out that numerically, one stable way of solving AX equal to B is to factor A using the QR decomposition, and then use this decomposition to solve AX equal to B. So I'll say more about using this to solve AX equal to B shortly. First, let's write down that we can decompose a matrix. So I'm going to state this for invertible matrices, but you can do this much more generally. So let's say we have an invertible matrix. Then there is a matrix Q with orthonormal columns and an upper triangular matrix R such that A is equal to Q times R. Okay, so you can sort of, in a 2x2 case, we know that Q is either a rotation or reflection composed with rotation. So you can sort of think of Q as being like an angle, and then R as being like the radius. And so you can think of this as being some sort of polar coordinates that you're putting on the space of matrices. Okay, that's sort of true. Okay, let's prove that we can do this. Well, we know that A is invertible. So that's equivalent to knowing that the columns of A form a basis of Fn. Okay, let's write A as the matrix whose columns are alpha 1 through alpha n. Now, I want to find this matrix Q whose columns are not just a basis of Fn, they're an orthonormal basis of Fn. And I start with a basis. Well, we know how to go from a basis to an orthonormal basis. We use Gram-Schmidt. So using Gram-Schmidt, we can find an orthonormal basis. Let's call it Q1 through Qn of Fn, such that the span of Q1 through, say, Qj is equal to the span of alpha 1 up to alpha j for all j between 1 and n. Okay, so this is Gram-Schmidt. At every step, the span is the same as the span of the columns we're looking at. We just have replaced those columns with orthonormal columns that span the same space. Okay, so having applied Gram-Schmidt, now let's let Q be the matrix whose columns are precisely these Qs. Okay, since the columns of Q form an orthonormal basis, of Fn, our first proof of today's lecture tells us that Q star Q is equal to the identity, right? So Q is unitary if we're working over the complex numbers, or is orthogonal if we're working over the real numbers. We'll just say unitary when we mean both possibilities depending on the field. Having found Q, we'll let R be Q inverse times A, or because Q is unitary, that's the same as Q star, Q adjoint times A. Right? Clearly, A is equal to Q times R by definition of R. So we just have to justify that R is upper triangular. Well, the jkth entry of R is Rjk. Well, directly from here, and arguing as we did at the beginning of class, this is equal to Qj star times alpha k. And that is just the standard inner product of alpha k with Qj. Okay, so now let's see what happens if j is greater than k, right? I want to show that this is upper triangular, so I want to show that if j is greater than k, I get 0. If j is greater than k, then alpha k is in the span of Q1 through Qk, and Qj is orthogonal to the span of Q1 through Qk. These facts together tell us that alpha k is orthogonal to Qj, and so Rjk is equal to 0. Thus, R is upper triangular. Okay, so that was pretty quick, right? We started with the matrix A. We know that its columns form a basis, so we can use Gram-Schmidt to get an orthonormal basis. And because Gram-Schmidt had this very nice property, the span of the first j elements is the same regardless of which of the two bases you're looking at, we were able to conclude that R was upper triangular. Now, if we want to solve Ax equal to b, right, as I said before, the theorem, we can use the QR decomposition. So let's say we want to solve this, and we've found the QR decomposition. Of A is equal to Q times R. Then we solve AX equal to B, which is equivalent to QRX equal to B, which is equivalent to R times X equal to Q star B. Now, since R is upper triangular, Rx equal to Y is quick to solve. By back substitution, okay, and moreover, great. So this is how you solve Ax equal to B if you have the QR decomposition, right? So you can compute the inverse of Q very quickly, and so this will be very quick. And then you're left with an upper triangular system, which you can solve very quickly using back substitution, as we saw when we studied the LU decomposition. Now, another advantage is that Q is an isometry. So Q star is also an isometry, right? Q is just the inverse of Q. Q star is just the inverse of Q. So multiplying by Q star does not change the length of vectors. So this first step where we multiplied by Q star, if you think about measurement error, like we did recently, so B might have a measurement error of H. Well, if you multiply by an isometry, then you don't change the size. So this multiplication doesn't make the error any worse, right? As we've talked about, multiplying by the inverse of A, you might make things much worse. So that's why this gives you something more stable, because when you've done this, you haven't messed up the error. You haven't made things any worse than they were given to you. And then backward substitution is also pretty stable, but yeah, anyway, that's the point. Let me remark that even here with invertible matrices, the QR decomposition is not unique. And there's a very simple reason for that. It's just an ambiguity in how you might have done Gram-Schmidt. Well, so Gram-Schmidt gave us these Qs, but notice that if I were to say multiply some of the Qs by -1, or if we're working with complex numbers by any unit complex number, any complex number of unit modulus, then I'll still have an orthonormal basis, and it will still have this property. And so R will still be upper triangular. So one way to make it unique, we could demand that all of the elements on the diagonal of R be positive. If we do that, then it is unique. But if you don't impose any requirement like that, then it's not unique. Okay, let's work out an example. So let's consider the system x minus 2y plus z is equal to 1, y plus z is equal to 0, minus x plus y plus z is equal to minus 3. Okay, now as we've mentioned before, in real life, if you're given a system of equations, well, you just do and you use Gaussian elimination to solve the system. But if you're going to be handed like the same coefficients and different right-hand sides, and you want to be able to solve various cases of that, that's when it's really useful to factor a matrix and then use that factorization for all of the subsequent systems. Okay, but in this case, we just want to work out an example of how you do a QR decomposition. So in this case, the coefficient matrix is this. So let's label these columns as alpha 1, alpha 2, alpha 3. Let's use Gram-Schmidt. To find Q1, Q2, Q3 orthonormal such that the span of Q1 through Qj is equal to the span of alpha 1 through alpha j for all j in 1, 2, 3. Okay, so Q1 is going to be just alpha 1 divided by its length to make it a unit vector. Right, so in this case, alpha 1, it's easy to see that its length is square root of 2. So I'm going to get 1 over square root of 2 times the vector 1, 0, minus 1. Right, there's our Q1. To find Q2, remember we do this in 2 steps. We find first Q2 tilde, and then we make it a unit vector. Q2 tilde is going to be alpha 2 minus the inner product of alpha 2 with Q1 multiplying Q1. So here that would mean minus 2, 1, 1. That's alpha 2. And then this coefficient alpha 2 inner product with Q1. Okay, well, alpha 2 inner product with alpha 1 would be minus 3. And for alpha 2, I'm just going to divide by square root of 2. So I get minus 3 divided by square root of 2. Right, that's the coefficient. And then Q1 is 1 over square root of 2 times 1, 0, minus 1. Right, and if we write that all out, we end up with minus 1/2, 1, minus 1/2. Okay, so that's Q tilde. Then Q2 is going to be Q2 tilde divided by the length of Q2 tilde. And that and so that gives us square root of 2/3 times minus 1/2, 1, minus 1/2. Okay, having found Q1 and Q2, we find Q3 in 2 steps. Q3 tilde is going to be alpha 3 minus, so you're going to do alpha 3 with Q1 times Q1, and then alpha 3 with Q2 times Q2. Okay, now in this case, if we look up here, this column is actually already orthogonal to this one and orthogonal to this one, right? So this column is orthogonal to the span of the first 2 columns. And since Q1 and Q2 span the same space as alpha 1, alpha 2, we see that alpha 3 is orthogonal to Q1 and Q2. So this is going to be 0, and this is going to be 0. And so we're just left with alpha 3. That means that Q3, which is Q3 tilde divided by the size of Q3 tilde, is just going to be alpha 3 made a unit vector. So it's going to be 1 over square root of 3 times 1, 1, 1. Okay, wonderful. So we found Q1, Q2, Q3, which means that we found the matrix Q. The matrix Q is going to have first column, 1 over square root of 2, 0, minus 1 over square root of 2. Second column is going to be minus 1 over square root of 6, then square root of 2/3, then minus 1 over square root of 6. And then the last column is going to be 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. Right. Another way of writing that, if you don't want to have too many fractions, is we could pull out a 1 over square root of 6, and then we have square root of 3, 0, square root of 3, minus 1, 2, minus 1, and then square root of 2, square root of 2, square root of 2. Okay, having found Q, we can find R as just Q star times A. So Q star would be 1 over square root of 6, and then every column becomes a row, or every row becomes a column. Right, and then the original matrix A, which had columns 1, 0, minus 1, minus 2, 1, 1, and 1, 1, 1. And if you write that out, you get 1 over square root of 6, 2 times square root of 3, 0, 0, minus 3 square root of 3, 3, 0, and then 0, 0, 3 times square root of 2. And we notice that that is indeed upper triangular. Okay, having found Q and R, we would now say, so to solve AX equal to B, and here B is 1, 0, minus 3. Well, this system is equivalent to wanting to solve Rx equals Q star applied to 1, 0, minus 3. Q star applied to 1, 0, minus 3 gives you 1 over square root of 6 times 4 times square root of 3, 2, and minus 2 square root of 2. So the system we want to solve is 2 times square root of 3 x. Well, here, let me not skip so many steps. So the coefficients matrix is now R, and R has this first entry. So I would have 2 square root of 3 divided by the square root of 6 times x minus 3 square root of 3 divided by the square root of 6 times y is equal to 1 over square root of 6 times 4 square root of 3. Right, that's what I get from the first row of R. From the second row, I get 3 over square root of 6 y is equal to 2 over square root of 6. And then from the last row, I get 3 square root of 2 z divided by the square root of 6 is equal to minus 2 square root of 2 divided by the square root of 6. So that's the system we want to solve. And because R is upper triangular, we can solve this by backward substitution, which means from the last equation, I'll find z. From the last two equations, I will find y. And then from the 3 equations, I will find x. So in this case is even simpler because we had some orthogonality already in the matrix A. But in any case, using backward substitution, we get, so from the last one, you can see that if you cancel out the this all of the square roots, you see z is just minus 2/3. From the second equation, cancel out the square roots. You see that y is equal to 2/3. And then plug y into the first equation, and you find that x is equal to 3. Right? And so there you go. Once you have q and r, it's very quick to solve the system of linear equations. Okay, so we'll stop there and pick it up from there next time.